So suppose we have a picture like this, and we have some data. So we have a dot here, and a dot here, and a dot here. We can ask a question, is the y value related to the x value? Is, in this case, husband's salary related to wife salary? So what we mean by that is, first of all, we could find the average first. Let's say we could find the average husband salary. We could also find the average wife. And we could use those to guess the salary of a randomly selected person. So we could say randomly select wife and guess what her salary is. So that would mean that each of these, remember we said that each of these dots represents a couple, and so the x coordinate of each of these dots is the wife's salary. So we can see that maybe I drew, let's say I have n, maybe I have 30 dots there. So let's say I have 30 dots there. That means I have 30 couples. And if I have 30 couples, that also means I have 30 wives. And so I could just collect all of the wives' salaries. That just means reading the x coordinate for each of these dots. So then I would have a bunch of wives' salaries. I could put them in a set. For example, I could have the first one maybe $50,000, the next one is $60,000, next one is $80,000, and so on. So I could just collect all of them, and I would have 30 numbers here for the 30 salaries of the wives. And then I could easily take those numbers and calculate the mean. And suppose I calculate the mean, and the mean is, let's just make up a number, the mean is $60,000. And let's say that right here is the $60,000 mark. So a lot of the salaries are less than 60,000, wives' salaries, and a lot of the salaries are more than 60,000. And then we could do exactly the same thing with the husband. And let's say this is the husband, and let's say the husband is 80,000 is the mean. Okay, so we could do this. And so if that's all the information you had, if you didn't have this picture, you didn't have these green dots, you just knew that the mean for the wife is 60, and you also knew that the mean for the husband is 80. And then I said, okay, now I'm going to go out on the street and find a couple, and I'm going to ask that couple, I'm going to speak to the wife. I'm going to say, what's your, and I'm going to ask you, not her, I'm going to ask you, the students here. I'm going to say, what would you guess is the wife's salary? So here, randomly select a wife and guess what her salary is. 60, right? Because the average wife's salary is 60. So why would you guess something else, right? It would be kind of strange to guess, oh, well, I'll guess, this wife, her salary is 100. No, I don't think so. Why should I guess 100 when the average is 60? I don't really have any reason to guess anything other than 60. So you would guess 60 for the wife, and you would guess 80 for the husband. So we drew last time these lines. Okay, so I'll draw a line here. So that's kind of like where the wife is. And then I'll have a different color for where the husband is, like this. So suppose that's the mean for the wife and the mean for the husband. Okay, now suppose that you can see this data. You can see these big green dots here. And now I'm going to ask you for the husband's salary, but I'm going to give you a little more information about the couple. I'm going to say that I'm talking about a couple where the wife's salary is here. So if the wife's salary is there, so let's say that's 20,000. So suppose we have a couple where the wife's salary is 20,000, and now I ask you to predict the husband's salary. So probably you're not going to say 80 anymore. So what might you say instead? Because we said, suppose we know that the wife's salary is 20 now, what would you guess the husband's salary is? So if I hadn't told you the wife's salary was 20, the best guess would be 80 for the husband. But now I'm telling you that the wife's salary is 20, and now somebody says, okay, I'm going to guess that the husband's salary is, like she said, I think 30. So it might be right. That might be a good guess. Anyway, it would be better than 80. So why did we change? Why did we change our guess? So how about if the data had looked like not this picture, but this picture? Okay, suppose the data look like this, and but we still have the same lines here, 60 and 80. Okay, so if we didn't know, if I didn't tell you the wife's salary, and I asked you to guess the husband's salary, you would still give 80. But suppose I tell you that the wife's salary is way down here. So the wife's salary is only whatever it was last time. What was it? 20. Now, what would you guess is the husband's salary? And you said 27 something? And why is that?
Because between 60 and 20, it's like 3 times wife's salary.
Right, right. Okay. Okay. So he said, well, this is the distance from here to here is from 0 to 60, and 20 to 60 is 2/3 of the way down, he said. So he said, well, I should go 2/3 of the way down here. So 2/3 of the way down here, he estimated, was about 27. That's an interesting, good answer, basically. Not the right answer, but it's a good answer. So he said something like, well, I'm going to guess that it's 27. But the thing is, he's not recognizing the important thing that I'm trying to show here. That is the difference between this picture and this picture. So what is the obvious difference between this picture and this picture? What am I trying to say with these two pictures? I drew these pictures. The second graph, I wouldn't say that the husband and wife salaries are related. Okay, well, what do I mean by that? I mean that if I know that the wife's salary is low, that doesn't give me any information about the husband's salary. The husband's salary could be way down here, but it could be way up here. Look at the people look at the couples whose wife's salary is 20, and you have all of these possibilities. There's no reduction in or there's no change in what I should predict, whether it's 20, 50, 60, 70, 80, 90. There's no reason why I should predict this high or this low. So for this picture, again, the best guess would just be the middle. For this picture, the best guess would just be 80. This data doesn't say anything about how to improve my guess. But here it definitely does. Here it definitely does. If the person if the wife's salary is 20, the spread is only like from here to here. So right in the middle of that might be about 30. So I wouldn't guess 80 in this case. because I know that the wife's salary is very strongly related to the husband's salary. So that's what I mean by related. A good indicator of what the y-axis should be, or I'm sorry, if you know the x-coordinate, that will give you a good indicator of what the y-coordinate should be. So if the x-coordinate is very low, I'm going to predict that the y-coordinate is also low. Now, we could also have a picture like this. So how about these? Are these related? The x and y coordinate, are they related?
Yes, they are related.
Yeah. In other words, if I know that very high, then I would guess that the husband is very low. So this gives me a lot of information. Because if this is high, I definitely would predict low here. So there's a lot of information in these green dots. We say they're very strongly related, or they're very strongly correlated, or not the dots are correlated, the two quantities, wife's salary and husband's salary, are strongly correlated here and also here, but not here. Here, the correlation is like nothing. We actually say here the correlation is 0, or basically 0 here for this picture. The variables husband salary and wife salary are not related here. Here, we're going to say the correlation is 0.88. So that's very, very strong. And here, it's even stronger, really. So here I might say the correlation is maybe, but it's negative. We say it's negative 0.93 or something like that. Just making that up. But this is more strong, actually, than this one. But it's just in the negative direction. The slope is positive here, but the slope is negative here. So we say negative 0.93. Now, if we had something like this data, we might say the correlation is 1, means perfect straight line relationship. So we might say the correlation. So what do I mean by that? That means that if I know the wife's salary, I can predict exactly what the husband's salary is. No, there's no play. It's not like could be up here and could be down here. If this is the wife's salary here, then I'm going to predict exactly this for the husband's salary. There's not going to be any guessing. The data is completely correlated. There's no mistake if I make this guess. Whereas here, we expect there's some kind of some error here. So if this is the wife, I'll predict I'll go up to here, and then I'll go over to here, and I'll say that's what I predict the husband is. But I recognize that it's more like between here and here. It's not I don't get a perfect prediction here. Okay, so this is not perfectly correlated, but this is perfectly correlated. So if it's a perfect straight line relationship like this, the correlation will be 1. If over here, the correlation is not perfect, and I said maybe it's 0.88. And over here, the correlation is not perfect either. It's better than the other one, but it's 0.93. In this case, negative 0.93. Okay, now the question is that we were working on last time was how do we measure correlation? Where do these numbers come from? So we have, let me take, say, which picture? I'll take this picture, but I'll add a few more dots here. Okay, so suppose we have that. And so suppose we have that. Now, where does this number come from, 0.88? So what we said, we can divide this up into quadrants. So I'll call this quadrant 1. I'll call this quadrant 2. I'll call this quadrant 3. And I'll call this quadrant 4. Okay? So now we can make some observations about the dots in quadrant 1, the dots in quadrant 2, the dots in quadrant 3, and the dots in quadrant 4. But we have to, first of all, we need a formula. And if you recall from last time, we had this picture here. We had this picture, and we had a formula here, this formula here. So let me take a snapshot of that. Okay, there. So we're going to think about this calculation. We can ignore this bottom part. We're not going to worry about that right now, but just the top. So you can see in here, I'll just write out those pieces. So you can see that we have a xi minus x bar there, and we also have a yi minus y bar there. So we want to focus on these. So remember, here's the x-axis and here's the y-axis. And here is x bar. We said that the mean for the x coordinates was here, and the mean for the y coordinates is here. So this line represents the mean for the y coordinates, and we draw a line here to represent the mean for the x coordinates. And then we're going to calculate for each dot. Remember, each dot, so here's a dot. So I could take this dot here, right here, and I could say, what's its x coordinate? Maybe this is what? Let's say 70. And I could say, what's its y coordinate for this dot here? And I would say it's maybe, let's say, make it 90. So I'm talking about this dot here. Okay, so if that's true, if I take this, the x coordinate, so this is the x coordinate here, call this xi, and this is the y coordinate, yi. So if you take xi minus x bar, so xi is 70 and x bar is 60, so 70 minus 60 is 10. But I don't care that it's 10. I just want to say that it's a positive number. So 70 minus 60 is a positive number. And then I can do the same thing for the y coordinate. 90 minus 80, that's also positive. So for a dot, and that's going to be true for any dot in quadrant 1. If I take any dot here and take its x coordinate minus x bar and its y coordinate minus y bar, for every dot in here, they're both quantities. Both of these are going to end up being positive. And so when I multiply them together, it's going to be positive. So what I'm doing here is I'm doing this for every dot. So I take a dot and I find its x and y coordinates, and I calculate this product here. And then I'm going to sum it up, means sum it up over all the dots. So not just this dot, but every dot. I'm going to do this. So whenever the dots are in quadrant 1, the things that I'm adding into this sum are going to be positive. Now let's talk about a dot here. Suppose we have this dot. So if we take its x coordinate and its y coordinate, so let's say this one has a x coordinate of, I'll just make it up, 50, and say this has a y coordinate of 40. So now if I want to do this calculation again for the purple dot, I'm going to take 50 minus 60. That's a negative. And I'm going to take 40 minus 80. That's also a negative. So when I multiply those two together, I'm going to get a positive. So whenever I take a dot in here and add its contribution to this sum, I'm going to get something where I have a negative times a negative. That's also going to give me a positive contribution to this sum. Now, what about quadrants 2 and 4, though? Are they going to give positive dots? Are the dots in quadrants 2 and 4 going to give positive contributions to this sum? Well, let's think about it. So let's take an orange done in quadrant 4. So let's say this one. What are its coordinates? So its coordinates might be, this might be 70 for the x. And this is going to be less than 80. So let's say it's also 70. So when I do this calculation for this dot in the quadrant 4, I'm going to get 70 minus 60, that's positive. But I'm going to get 70 minus 80, that's negative. So when I multiply these two together, that's going to give me a negative contribution to this sum. So in quadrant 4, that's true for every dot in quadrant 4. So it's going to give us negative contributions to this sum. And what about here? So let's take one more. So let's take this one, a dot here, so like this one. So if we look at its coordinates, the coordinates of this dot, the x coordinate is going to be less than 60. So let's say it's 50. And the y coordinate is going to be more than 80. So let's say 90. It's really not 90, but let's say 90. So now when we do this calculation for a dot in this quadrant, we're going to hit 50 minus 60 is going to be a negative, but 90 minus 80 is going to be a positive. So that's going to be a negative times a positive here, and that's going to give us a negative contribution. So if a dot is in this region, it's going to give a negative contribution. Okay, so with all of that, we see in here we're going to get positive, here we're going to get a negative contribution, dots in here are going to give us a positive contribution, and dots in here are going to give us a negative contribution. So what about if we had this picture like this? Well, if we drew these lines here, so where are these dots? These dots are all in either quadrant 1 or quadrant 3. Maybe I didn't really draw it that well. This should be up higher. So excuse me for doing that. But basically you can see what I'm trying to say, which is here's quadrant 1 and quadrant 3. And what I was trying to show, although I didn't do it very well, is that all the dots are going to be either in quadrant 1 or quadrant 3. That means they're all going to make positive contributions to this sum. Now, what if the dots weren't like that, but they were like this? For the red dots, if we had data distributed like the red dots, what would the contributions be, positive or negative?
Negative.
Negative. They would only give negatives. So when I do this sum for the green dots, I'm going to get all positive numbers in here. So this is going to be, for the green dots, this would be a large positive number. For the red dots, all the contributions are going to be negative. So this would be a large negative number if I did it just for the red dots. Now, what happens if the dots look like this? Then what? I'm going to get a lot of positive here, a lot of negative here, a lot of positive here, and a lot of negative here. So what's the total going to be? Remember, we're talking about this sum. We have two parts.
Would it be 0?
Yeah, it's going to be like 0 because I'm going to get a lot of positive numbers from these dots in this sum, and then a lot of negative numbers from these dots, then a lot of positive from these, and a lot of negative from these. And when I add up all those numbers, I'm going to get a lot of cancellation. So this is now, for this kind of configuration, this sum is going to be close to 0. Okay, but for the other ones, it was going to be, here it was going to be very large positive number, and here, for the green dots, it's going to be a very large positive number. For the red dots, it's going to be a very large negative number. So this sum tells us a lot about the configuration of the dots. So if I get like perfect positive correlation, this sum is going to be big. If I get perfect negative correlation, this sum is going to be a large big but negative. But if I get no here where this is no correlation in the data, this sum is going to be 0. So this sum is very important in terms of what kind of relationship the two variables have. Here, the two variables have no relationship, and this sum is 0. For the green dots here, they have a very strong relationship, and this sum is going to be a big number. And here, when dots look like these red ones, which means there's a very strong correlation but negative, this sum is going to be a big negative number. Now, there's just one little problem with this summation here, and that is, maybe like in this green one, I might get, suppose for the green one here, when I do this sum, I might get 1,000. Let's just make that up. And if I did it for the red one, let's say, I might get, let's say, negative 1,000, for example. But those numbers, 1,000 and negative 1,000, those are kind of like sort of arbitrary. They kind of depend on how many dots are there. So I don't really want that. So I like the fact that this is very large and positive. I like the fact that this is very large and negative, but I prefer that this calculation always be between this calculation or the calculation I do, I would prefer that it's always be between -1 and +1. And these are not. This is like 1,000 and -1,000. They're not always between -1 and +1. I want to construct something like this, but that only goes as high as +1, not as high as 1,000 or 10,000 or 10 million, and only goes down to -1. So that if the relationship is perfect, like these green, it'll be 1. And if the relationship is perfect, but like these red, but negative, it'll be -1. So I'd like to have this calculation, but to kind of scaled down so that it's always between -1 and +1. And that can be done by this. Taking this and dividing it, not by this, not this, that's not what I'm going to do, but dividing it by, no. Okay, so I'm going to divide it by, so I'm going to use this calculation, but I just want to scale it down. So the way the good thing to divide it by is, what does this notation mean? I think we have this. What does this one mean? What's this mean? Can anybody tell me what that means? It's the standard deviation. This is the standard deviation, and this is the standard deviation. So do these mean the same thing? Does the one with the purple mean the same thing as the one with the orange? Sigma y. So they're not the same, right?
Yep.
So what does sigma x mean? The standard deviation for the x data. Remember, we have each of these dots has an x coordinate. Or we can say each of these dots has a wife's salary. So we have all the wives' salaries, and we can calculate the standard deviation of their salaries, right? We can take all the wives' salaries and calculate their standard deviation. Why not? We just collect them and then put them in Excel and calculate the standard deviation. And then what else can we do? What does this stand for?
Standard deviation for y.
The standard deviation for y, and in this case, y is the husband's salary. We can also take all the husbands and ask them what their salaries are, put that into Excel, and calculate that standard deviation. So what am I saying? We said that this sum here is really important for telling us what the relationship is between the two variables, whether they're correlated or not, and how strongly correlated are they. So are they correlated like 1, or are they correlated like, what did I say this one was? Are they correlated like 0.88? Are they correlated like 0.93? This was really important for doing that, but it wasn't bounded. So this could be as high as 1,000, or as low as negative 1,000, or even larger than 1,000. It could be, it's just can get really big. We don't really want that. We want to make sure that the calculation is always between +1 and -1. This will do that. If you put these two in the bottom, divide by these two, that scales everything down. And it will scale it down to exactly between -1 and 1. So the green one, when we do this calculation, will be, if I drew it perfectly, will be 1. The correlation will be 1. And the red one, if I drew it perfectly, the correlation will be -1. So this is the correlation coefficient, it's called, or this is this number, 1.88. These are called the correlation coefficients. Correlation coefficient is -0.93. Correlation coefficient is 0.88. Correlation coefficient is 1. Correlation coefficient for the red one is -1. Correlation coefficient for this one is 0. Okay, and what's the calculation for the correlation coefficient? It's right here. Okay, so this, now maybe I shouldn't have used sigma here. I should have used S sub x and S sub y, because maybe I'm only talking about a sample of data, and I only used x bar here and y bar, so I guess I should have said S sub x and S sub y. If I had used mu x instead of x bar here and mu y instead of y bar, then I would use sigma and sigma. So maybe I shouldn't have put sigma in there. I should have used S. But anyway,